Hello viewers, welcome to the next section of this course, Defining Testable Code. In this section, we will look at some of the topics such as understanding testability, white box testing, code coverage, TDD with palindromes. Now let's move to the first video of this section, understanding testability. In this video, we will look into the different aspects of software testability in detail. The testability can be defined as the degree of ease with which a software system exposes its faults through execution-based testing. Ideally, a good software system should have high level of testability. Now let's see software testability and related attributes. A software system is testable if it gives up its faults easily to the tester. Not only that, the system should behave in a predictable way for the tester to develop useful tests. An unpredictable system would give varying outputs to a fixed input at varying times, hence, is not testable or very useful for that matter. More than unpredictability, complex or chaotic systems are also less amenable to testing. For example, a system whose behavior varies widely across a spectrum under load doesn't make a good candidate for load testing. Hence, deterministic behavior is also important to assure the testability of a system. Another aspect is the amount of control that the tester has on the substructures of the system. In order to design meaningful tests, a system should be easily identifiable to subsystems with their well-defined APIs, for which tests can be defined. A software system that is complex and doesn't provide easy access to its subsystems, by definition, becomes much less testable than the one which does. This means that systems which are more structurally complex are more difficult to test than the ones which aren't. Let us list this down in an easy-to-read table. You can easily come to the conclusion that a system with high testability is a system with high determinism and low complexity. Now let's look at the topic, testability, architectural aspects. Software testing generally implies that the software artifact being tested is being assessed for its functionality. However, in practical software testing, functionality is just one of the aspects that can fail. Testing implies assessing the software for other quality attributes, such as performance, security, robustness, and so on. Due to these different aspects of testing, software testability is usually grouped at different levels. We will take a look at these from the point of view of software architecture. Different aspects of software testing are functional testing. It is further classified into white box testing, which is done by developers as unit tests, and black box testing, which is done by QA engineers. Next one is performance testing, which is further divided into load testing, stress testing, scalability testing. After that, we have security testing. Then usability testing. Next is installation testing. And finally, we have accessibility testing. These are various other types of software testing, which involves different approaches and are invoked at various phases of software development, such as regression testing, acceptance testing, alpha or beta testing, and so on. Testability strategies. Reduce system complexity, improving predictability. Control and isolate external dependencies. Control and isolate external dependencies. Tests usually have some sort of external dependency. For example, a test may need to load, save data to or from a database. Another may depend on the test running on specific times of the day. A third may require fetching data from a URL on the web. However, having external dependencies usually complicates a test scenario. This is because external dependencies are usually not within the control of the test designer. In the aforementioned cases, the database may be in another data center, or the connection may fail, or the website may not respond within the configured time, or give a 50x error. Isolating such external dependencies is very important in designing and writing repeatable tests. The following are a few techniques for the same. Data sources. Most realistic tests require data of some form. More often than not, data is read from a database. However, a database being an external dependency cannot be relied upon. The following are a few techniques to control data source dependencies. Using local files instead of a database. Quite often, test files with pre-filled data can be used instead of querying a database. Using an in-memory database. Rather than connecting to a real database, a small in-memory database could be used. Using a test database. If the test really requires a database, the operation can use a test database, which uses transactions. Resource virtualization. In order to control the behavior of resources which are outside the system, one can virtualize them. That is, build a version of these resources which mimic their APIs, but not the internal implementation. Some common techniques for resource virtualizations are stubs, mocks, and fakes. Stubs. Stubs provide standard, canned responses to function calls made during a test. A stub function replaces the details of the function it replaces, only returning the response as required. For example, here is a function that returns data for a given URL. And this is the stub that replaces it, which internalizes the external dependency of the URL. A more common way to write such a function is to combine both the original request and the file cache in the same code as shown here. The URL is requested just once the first time the function is called, and in subsequent requests. The data from the file cache is returned. Mocks. Mocks fake the API of the real-world objects they replace. One programs mock objects directly in the test by setting expectations, in terms of the type and order of the arguments the function will expect and the responses they will return. Later, the expectations can be optionally verified in a verification step. Fakes. The fake objects have working implementations but fall short of production usage because they have some limitations. A fake object provides a very lightweight implementation which goes beyond just stubbing the object. For example, here is a fake object that implements a very minimal logging, mimicking the API of the logger object of the Python's logging module. The fake logger class implements some main methods of the logging.logger class, which it is trying to fake. It is ideal as a fake object for replacing the logger object for implementing tests. Here we have come to the end of this video. In this video, we have learnt about the aspects of software testability.